So we will start with quantum mechanics 2, and the syllabus is per syllabus. This is starting from chapter 5 of the second edition of Introduction to Quantum Mechanics by D.J. Griffiths. And the chapter is Identical Particles. We will start with the section 5.1, which is a two-particle system. So far in quantum mechanics, we have studied single particle system, or a particle, the system which were based on one particle. Now we will go on with the many particle system. So the minimum is 2 and 2 or more than 2 particles. This will be sort of a coupling type, or the configuration will be coupled. So first we will have to understand what is meant by identical particles. Identical means same particles. Particles are different, but they are same. We cannot recognize them. We call them indistinguishable particles. So we will have some statistics for them. For example, distinguishable particles and indistinguishable particles are identical particles. We will also discuss symmetric and antisymmetric as well, wave functions. So let's start with the two-particle system. And in two-particle system, I know that the wave function I was writing earlier is psi of r. Psi is a function of r for time independent, and for time dependent I was writing it as a function of r and t. Now, is my wave function will not be of a single particle but two particles. So I will write this one is psi r1 and r2. And if it will depend on time, then this will be r1, r2 and time. Time is the same for both the particles. There is no t1 or t2. The Hamiltonian will become, so I will not write the earlier form now. You know that thing. Then it was minus h bar square over 2m del square psi plus v of r psi, and this will now become del 1 square psi, and so psi I am not writing, only writing the Hamiltonian, minus h bar square over 2m for the second particle, and plus v of R1, R2 and T. So the potential for both. And this will be means we will be solving the Schrödinger wave equation I h bar curly psi over curly t, and this is equal to h psi. And this is the time-dependent Schrödinger wave equation. We will solve for this psi such that this psi is now psi r1, r2 and with time. Similarly, the normalization condition was that psi mod square dx in one dimension or dr in 3 dimension. dr, this is equal to 1 in all space, minus infinity to plus infinity, this is equal to 1. Now this normalization condition will come out to be all space, and psi will become r1, r2 time and mod square. So d cube r1, d cube r1, d cube r2. Now, from the d cube Why I am writing dq? Because three dimensions of r are there, x, y, and z. Earlier we were writing this is dx. So dx is equal to 1. Now this will be dx, dy, dz. So three dimensions. And here I will write this one is dq r1, r2, and this will be equal to 1. So I will have the normalization like this, and the time dependent psi r1, r2, and t. You can put a vector sign here because these are vectors, but I am ignoring it. You can continue by writing it. This is equal to sine r1, r2, and for time component I can write minus IET. This is the time evolution of our wave function. So this is the spatial wave function and this is the time component. Similarly, I can write the Schrödinger wave equation, which is the time independent, minus h bar square. Okay, we will have to take care of one thing here. This is a two-particle system. So if the two masses are not the same, then I can write here m1 and m2. So this will be 2m1 and del 1 square sine minus h bar square over 2m2 del 2 square sine plus v of sine is equal to e sine. And we will have to solve now such an equation. Now let's start with two types of particles, and the two types of particles are bosons and fermions. We will discuss them one by one, and you will have to see that these are two different types of particles, so their configurations will be different. Now, when the particles will be identical particles, and whether they are identical bosons or they are identical fermions, you will have to understand the fact as well that some of the phenomena which are purely quantum mechanical, we cannot visualize it classical mechanically. Means they are not the classical phenomena so that we can visualize them. We are dealing with quantum mechanical particle. Let's say I am considering in fermions, and in fermions we are dealing with electrons. Now electrons are identical particles. Classical objects, we can give label to them, we can give different colors to them so that we can recognize that I am placing one particle in one level and the other particle in the other level. And I can say that this is one kind of configuration. For example, I am having this is a two orbit or two state system, and here in this system I have placed one particle which is a classical particle. Let's say this is red, and this particle is, let's say, blue. So this is one configuration. I have placed one here and one here. I can place both the particles here. I can place both the particles here, and I can place red here and blue here, and then red here and blue here. So many configurations are possible if the particles are distinguishable. If I can label them, if I can color them, or any other way of recognition I can do. But if the particles become identical, means I cannot label them, or they are the same particles. Let's say both are red balls, the same balls. Then the number of configurations will decrease. Configurations means how many ways you can put those particles. Now the number of configurations will decrease. I can put both here, I can put both here. That is possible, one configuration. Now if I place it one here and one here, and this one I move here and this one I move here, it's the same configuration. Clear? So from the 4 configurations, we have come to the 3 configurations. Got it? When the particles became identical particles. Now if the particles, I impose another conditions on these particles, then let's say these are fermions, like they are electrons and protons. Consider they are electrons. Now if I place one electron here and one electron here, I switch them. Now they are identical. So the switching will not generate any new configuration, but it will be the same configuration. I cannot put 2 here or 2 here, because you know from the Pauli Exclusion Principle that 2 electrons cannot have the same state, the same quantum state. So the number of configurations has further decreased, right? So one thing is when the particles are distinguishable particles, then it will have one kind of configurations, and when the particles become identical, they will have less configurations than that. And when in the identical particles, the particles become bosons, they will have one type of configuration, and when they become fermions, the number of configurations will be different. So the purpose behind studying in this chapter is that how many configurations we can have, how we can place the particles. So we will start from the scratch, and then we can go to the different type of configurations which you call the distributions, like the Fermi-Dirac distribution, Bose-Einstein distribution are configurations. So our final aim is there. But we will start from a very scratch, and we will develop some mathematics, and we can apply that mathematics in order to go to a complex configuration. Clear? Now, tell me one thing. Whether the electrons are identical particles, can you recognize one electron from the other? Yes. Someone said by spin, we can recognize them. One will have spin up and the other will have spin down. So we can recognize them from spin. They will become distinguishable. True?
Yes, sir.
But the answer is no. Why? Because I have told you earlier as well. This electron is with spin up and this electron is with spin up. Now, when they are in their configurations, when they are in their states. So, in one state, one electron, for example, we cannot say which of the electron is spin up and which of the electron is spin down. We cannot say this thing. We can only say that one electron is with spin up while the other electron is with spin down. We cannot say which one. Clear? The other thing is, when it is spin up and you do a measurement on this electron, then it will change its state. It will become spin down. Clear?
Yes.
So you have seen in the ladder operators, the L plus minus, the S plus minus, they are changing the states. LZ are the projection operator, are SZ, they are not changing the states, they only change the eigenvalue from plus to minus. While measurement of the S operator on a system will means the same thing. Inside a nucleus you are giving proton and neutron. You combinedly call them as nucleons. So as long as they are inside a nucleus, you cannot say which one of them is proton and which one of them is neutron, because they are constantly exchanging particles. You cannot recognize them. That's why you give it a common name, nucleon. They are nucleons. In the same sense, you cannot say which electron is with spin up and which electron is with spin down. So electrons are completely identical particles, or we can say indistinguishable particles. They are having some statistics with them, and we will start with some simple mathematics and we will go to those statistics. So let's say from particle I don't mean now electron or any boson particle. From particle I mean just particle. Then I will apply on that particle whether it is identical or it is not identical, like it is distinguishable or indistinguishable. Then on those means in indistinguishable I will apply whether they are bosons or they are fermions. So these statistics means we will apply one by one. Let's say we are having one particle in one state. One particle is in state psi A R, and another particle, which is particle 2, it is in a state psi B of R. These are the spatial coordinates. R the spatial coordinate. Psi A we designated to one particle, and psi B we designated to another particle. We are not considering which particle. We are just saying one particle in the other particle. So their combined state you can write as psi R1, R2. And this will be equal to, if I combine them, means the generalized form, this wave function, it will be the product of the two. And it will be equal to psi A R1 and psi B R2. Clear? R1, R2, R1 and R2. And now there are some states which you can separate, and some state they are not separable, means you cannot separate them out. For example, we have studied the singlet and the triplet states earlier. Singlet and triplet state. Now in singlet state, we are having one state only. That's why we call it singlet. In triplet, we are having three states, and each of the state is a separable state. It means you can separate them, three states, 1, 2, 3. Now, one state which you call a coupled state. So coupled state you cannot decouple, you cannot separate it out. And let's say I write one of the state in which we are having a combination like psi 1, 2. It's a singlet state, and you remember what it was. It was spin up, spin down, minus spin down and up. This was our singlet state. You remember this one. Now this is for our particle 1, this one for our particle 1, and this was for our particle number 2. This for particle 1 and for particle 2. Now can you separate this state? Can you write like psi 1 is 1 over 2, then up and down, plus this? No, we cannot. We cannot split it. It's a singlet state. It's a coupled state. So, we can not say that which particle is spin up and which particle is spin down. We cannot say about the spin. So, in this way, we will have to write the